So Michaelis-Menten kinetics is one method to treat the kinetics of a catalyzed reaction. So these were originally used for, often used for enzyme kinetics. Like I said, enzymes are the catalyst side of biology. So this is often used in biochemistry. But this approach can also be used for other types of catalytic reactions. So what the Michaelis-Menten kinetics kind of assumes is if you have your substrate plus your catalytic amount of enzyme, and then so this could reversibly react to form this enzyme substrate complex, ES. And then in a second irreversible step, then we release our enzymes, right? Because the enzyme is a catalyst, it has to be able to turn over. So this is the turnover step. And then it forms the product. So this is a kind of two-step process. And this looks really familiar to the treatments that we were talking about before for steady state and pre-equilibrium. So we have our rate constants, forward reaction, reverse reaction of this reversible step. And then K2 refers to the second irreversible step. So again, this is substrate, enzyme, aka our catalyst. This is our complex. And then P is our product. So the key part about the Michaelis-Menten kinetics is it uses the steady state approximation that we used before, but the additional part that it also assumes, or I guess this is true for catalytic reactions, is that we have our initial concentration of catalyst, our enzyme total, and then the total amount is going to be the sum of all the E's within our equation. So it's got to be a sum of plus this enzyme substrate complex. So this has got to be true at all times. And then so if we know this is our total concentration. This has got to be constant. And then we'll be able to then express our concentration of enzyme at any given time as a difference between E total, the constant, and ES. So at any given time, E equals E total minus ES. OK, so the Michaelis-Menten approach, like I just said, was that we use the steady state approximation, which, if you remember, is that this intermediate ES doesn't build up and reacts very quickly. So because of that, then our approximation is that the change in the concentration of the complex over time equals 0. And then we can then use our elementary step rate expressions to figure out what this is, and then solve for our overall rate law. So this is going to be the equation of complex. Going to be K minus 1 ES minus K2 ES. So this just comes from this mechanism. OK, and then now we substitute this equation into here. And then let's see. Let me make sure I get this right. So this equals 0. So this means that K1 S times E total minus ES minus K minus 1 ES minus K2 ES equals 0. OK, so there's that. And then now we can just solve for the concentration of the complex. So here we have ES equals, let me make sure I get this right, K1 E total times S over K minus 1 plus K2 plus K1 ES. Oops. Did I make a mistake? I meant to say S down there. That's an S. Okay. S. Very good. So this is our expression for the complex concentration. And the reason we want to find this is because if you want to find the rate of the formation of product, our overall rate is going to be equals K2 times ES. And then so we just multiply that out. And then so this gives us, let's go up here. So then dP over dt equals K2 times concentration at ES. So this is going to be K1, K2, E total times the substrate concentration over K minus 1 plus K2 plus K1 times the substrate concentration. Okay, so this is our rate law. Okay, so there's one kind of approximation. You can kind of factor out a fraction. So if we set this fraction, K minus 1 plus K2 over K1, this is what's known as the Michaelis-Menten constant. Sorry, the Michaelis constant, rather. Michaelis constant. So this is, of course, just some expression of our rate constant, which is why it is a constant. And of course, it's another K. For some reason, this is big K. In any case, so you get this by sort of dividing both your numerator and your denominator by K1. And then so then you can express dP dt now as K2 E total substrate. And then this is the fraction where we divided out Michaelis constant plus S. Okay, so this is our expression. Let's actually look at how this looks once we plot it. Sorry, I'm going to erase on this side. Okay, so again, our rate expression is only in terms of some expression of our rate constants, our total enzyme concentration, and substrate. So we have a good rate law because we don't have anything in terms of an intermediate, just of reactants that we know. So we can see how the rate should vary if we change things like, let's change the substrate concentration, and then the rate. So if you look at this expression, so at low substrate concentration, if it's very low compared to Km, then this will be approximately Km in the denominator. So this will approximately be first order in S, because the expression, so at low S, dP dt would be K2 over Km, oops. And of course, the total enzyme concentration is a constant. So this will be first order. At higher substrate concentration, right, so the S would then dominate the denominator, and then this would both cancel out. And then so dP dt would be, right, this would cancel out. This would be K2 E total. And that would just be the rate. So this will be zero order in substrate. So what this means is that as we're plotting and changing the substrate concentration, the rate of our reaction should change in this manner, where it would be originally linear, and then it would plateau off. So this plateau, this value of the plateau where it crosses, this is our so-called oops, let me get a different color. This is so-called Vmax. So at this, where it's plateauing, at high substrate concentration, our rate is going to be equal to, again, K2 E total. Okay, so that's the maximum rate that we could get out. So, you know, it'll be dependent on how much catalyst you put in. That makes sense, right? The more catalyst you put in, the faster it should go. At low substrate concentration, right, this will be substrate dependent. And then, of course, our slope over here should be K2 over Km E total. Okay. So this is one way to plot our enzyme kinetics. Another interesting point would be to see whether we could linearize. So if we take, sorry, I'm trying to fix my marker here. If we take 1 over the rate, so 1 over this expression, what we get out is going to be equal to, right, this would be Km plus S over K2 E total S. And then so this is going to be equal to, right, we could have some expression Km over K2 E total. So these are all constants. Km is a constant because it's an expression of K1, K minus 1, and K2. Here's K2, and the total enzyme concentration is also a constant. So this will be times 1 over S plus, okay, and then if we, so we're splitting apart this numerator into separate fractions, and this will be 1 over K2 E total. So you can see this is a linearized form where our x value is 1 over S. Here's our y value, 1 over rate. So 1 over rate. And then so we could think about plotting this. Sorry, just try to, there we go, here. So if we plot this, we could plot our 1 over S, and then this would be 1 over rate. And then this should be linear. And then so we should get out something that looks like this. And then so this slope equals, right, this will be Km over K2 E total. This intercept is going to be 1 over Vmax, because if you remember, Vmax equals K2 total enzyme concentration. And then if we extend out to the negative region, this x-intercept is going to be -1 over the Michaelis constant. So by doing this linearized form, you can get out quite a lot of information about your catalytic reaction. Okay, and then in class, we'll do an example of how to apply these catalyst kinetics to a catalytic reaction.